assume that we have an identity which is 5x squared minus 6xy plus 5y squared. This is equal to 2. Now, this is an identity which is telling to us a relationship between different values of x and y. And let's say that we are given this expression, and we have to show how the x and y depend. And a good way to do this is to analytically draw the graph. Okay, so this is one of the options where we can get a better insight of this equation. If we use a graphing machine or a programming language, they do this automatically. But sometimes we can also use a little bit of our intuition of how to do this. Now, at least since we are in the course of linear algebra, we always said that using the principles of linear algebra, they are very useful to simplify the data or to get much more insight on the data. And also all the principles that we cover, they are very helpful. Now, when we talk about linear algebra, the first question that might come to your mind is the following. This is an expression which is not linear because we have x squared, we have the coupling of the x and y, we have also the y squared, so this does not look like a linear expression. So how can linear algebra become useful at this point? Okay, how can we include a matrix here? So this is a valid question, but in different areas of engineering, what you might often see is representing complex expressions trying to use also linear terms in this form. So you can have a vector x transpose times a matrix A times the vector x again. This is equal to 2. Okay? So this is an expression which there is some linearity in it because we only have x's and matrices. We don't see x squares and y squares very explicitly. So the first question is it possible for us to rewrite this expression as this term in here? Okay, can we do that? And let's see what is the vector x. Vector x in this case is going to be the x and y, the little x and y. And the x transpose, this is going to be xy, right, like this. So x itself, it's 2 by 1. X transpose is what? Is 1 by 2. So here. And then let's see how we can write this. We can denote in this part that here we have x and y, which is a matrix 2 by 1, times a matrix which is 5 minus 3, 5, which is 2 by 2, times the vector x and y, which is 2 by 1. This is equal to 2. And this scalar number, 2, is also 1 by 1. So if we multiply, sorry, no, this is wrong. What is wrong here? Can you notice it?
1 times 2.
That's true. I miss it. So this is 1 by 2. So it is 1 row and 2 columns.
And when we multiply them, will be 1 by 1. It is a scalar in the end, I think.
That is true. So apparently, we can write it like this. Okay.
Professor, one question. For example, in this example, we have the coefficients 5, 5, and minus 6. And I can guess that the matrix will have 5 minus 3 minus 3, 5, so that when we multiply, we get the equation in the end. But how about in some cases when we have coefficients like 3, 4? How do we find that matrix? Or it is that given?
No, you have to find it. It depends on the problem, okay? Well, it depends on the problem, and you might have to come up with smart approaches. And you try to do your best to represent it like this, okay? Maybe they don't always...
But in this example, how did you find the matrix, or you guessed?
Well, let's see. First of all, let's check whether this is true. I mean, this could be wrong. But let's see this one. So if we multiply the matrix with an xy, what do we get here?
5x minus 3 epsilon?
Yes, so it's 2 by 2 times 2 by 1. We should get a 2 by 1, right?
Yes.
So 2 by 1, this is 5 times x, right? Minus 3y, minus 3y. This is a single number. Then we have
minus 3x plus 5y.
That's true. Plus 5y. Okay. Here we have a vector which is 2 by 1. We multiply this one with x and y. And this is 1 by 2. That's fine. So what do we get here is that x multiplies with this the first term. So we get 5x squared.
Minus 3xy.
Okay. And then we have
minus 3x squared plus 5y squared.
That's correct. Plus 5y squared, 5y squared. So we confirm this looks good, okay? So minus 3xy, we get minus 6xy. So we are fine, right? And so apparently we are given this identity, which is not linear. We have x squared, y squared, and 6xy, but we used our knowledge of linear algebra to represent this expression like this, and then we decompose it, we nicely write this using the symmetries that linear algebra provides for us, and this is what we get. Now, if you allow me, I can delete this one because this is almost straightforward, okay? So we multiply this, we get the equal to 2. It is the same expression. Now, what we can do here, so it looks like we have x and y, and x and y, we know where they are. Okay, so let me use this part of the, wait a second. You can see up to here, okay. So here, we have a basis. Here we have x and y. That's good. So now, let's assume for a moment, let's rotate the x and y by 45 degrees. If we do that, we're going to get, so this is a new basis, which is capital X. And here we have another major coordinate axis, which is a capital Y. This angle here, it is 45 degrees, or pi over 4. So what is a matrix which can, which rotates the axis by 45 degrees? What is it?
Cosine P4 minus sine P4, sine P4, cosine P4.
That is true. So let's assume for a moment that we are in a standard basis where the basis elements are 1, 0, 0, 1. And we want, and in the standard basis, the values that we are given, they are x and y. So we are talking about the first expression, where these are x and y. And let's say that we want to go to a new basis by rotating the axis by 45 degrees, and we get this xy. So, and how are these two related? Who can help me here? How is xy, this capital XY related to xy?
We can write x equals 1 over the square root of 2.
X is equal to 1 over square root of 2, y?
Which multiplies x capital minus y capital.
But how do you get it? So if we use the transformation using the matrices, the transformation matrix, how are these two related?
When we can multiply 1 over the square root of 2 with the matrix 1 minus 1, 1, 1, because you said you were going to rotate it 45 degrees.
Yes, that is true. So allow me to write this one. So we have a matrix A, which rotates by pi over 4, and this would be equal to cosine pi over 4 minus sine pi over 4, sine pi over 4, and cosine pi over 4. Now, all of these values, they are equal to 1 over square root of 2 times
1 minus 1, 1, 1.
Yes, 1 minus 1, 1, 1. So this is the matrix P, and we know that this matrix P here, which is the how we are going to change the x and y, this is how we apply this matrix P on this basis, okay? Because it might be confusing where we apply it, but we know that always the standard basis, we obtain the standard basis, by the vector by multiplying the matrix P. Actually, you know what the P is, it's already here. So this is equal to 1 over square root of 2, 1 minus 1, 1, 1.
And we multiply it with xy.
That's correct, with capital X, capital Y. This is the relationship that we have here for X and Y. This means that the little x, this is equal to 1 over the square root of 2 multiplied by the capital X minus the capital Y. And the small y, this is equal to 1 over square root of 2 capital X plus capital Y. Okay, so here we found what is the little x and the little y. And by the way, we are in the standard basis. And for this identity here, we have here 5, minus 3, and 5. Okay? So let's not forget, so we are dealing in a standard basis. This is the general picture. Now, we want to go to a new basis because we want to simplify things. And let's move carefully. And allow me to erase this one because this does not carry too much essential information. It was clear why we wrote the x and the x transpose. And now, with this change of variables, where x is defined like this, we can
substitute them to the first equation.
That is true. And this would make something like this. We have 5 times x squared. This is going to be equal to 1 over 2, x minus y squared. So here we get x squared minus 2xy plus y squared minus 6xy. So if you multiply 6xy, x times y, we get here 1 over square root of 2 times 1 over square root of 2. This is 1 over 2 multiplied by
x minus y.
Yes, times x plus y. So this is like a plus b times a minus b. It is equal to a squared minus b squared. So here we get x squared minus y squared. Then we get plus 5y squared. 5, 1 over 2, y squared. This is 1 over 2, x plus y squared. X plus y squared, we get plus 2xy plus y squared. This is all equal to 2. So let's gather the common terms. Here we get an x squared, which is 5 over 2x squared plus 5 over 2x squared. This is 5 minus 3x squared, we get 2. So we get 2x squared. And then
Professor, why don't you multiply it with 2 so that you can get rid of the radio 1 over 2 and you will get 6?
I can do it. Yes, that's true. But let's move on. Let's move ahead like this. Okay, you are right. But we can cancel it later. So the x squared terms, we got done with it. And then let's have a look at y squared. Here we have 5 over 2y squared plus 5 over 2y squared. We get 5y squared plus 3y squared. We get plus 5 plus 3. This would be plus 8 y squared. And here, this minus 2xy times 5 over 2, this is plus 2xy, so they cancel out. So these are all the terms that we need, or that we have in here, and this is all equal to 2. So now, we did a change of variables, and this identity here, it can be rewritten in this form. So now, let's try to write this expression for this new identity, and this one, it can be written as, this is capital X, capital Y, times the matrix, which is 2, 0, 0, 8.
Or 1, 0, 0, 4.
That is true, but then we would divide the 2 by 1, right? So this would be equal to 1. But for the moment, this is like this. Is it good?
Yes.
So, one thing that we might have a look into is that this matrix here, the matrix A, this is This is diagonalized now, okay? So if we see a diagonalization, this is like a good sign because that's what we use the linear algebra for, okay? So this is what we obtain, and then what we can do next is let's have a look and let's see what is the graph of this one. It looks like this expression here. It should be relatively easier for us to draw it in the new pair of axes, which is shown here in red color. So we have the capital X, we have the capital Y, and let's draw it. So to figure out what the graph is going to look like, let's assume what happens when x is equal to 0. When x is equal to 0, what do we get? We have 8y squared. This is equal to 2, and this means that y squared is equal to what? 1 over 4. This means that the capital Y is what? It's 1 over 2, right? So if this is 1 over 2, this is 1, this is 1 over 2, and here we get also minus 1 over 2. So this is, but then when y is 0, we get 2x squared. This is equal to 2, which implies that x itself is equal to plus minus 1. Right? So plus minus 1, we get here, this is half, this is 1, this is half, this is minus 1. Then we get something like this. So here we get the equation of an ellipse. Okay. So it looks like with this variable change that we did by rotating the angle by 45 degrees, we obtained a new representation of the data, and it is much easier for us, and it is also very intuitive to draw the graph. And apparently we learned something more here. Okay. Now the thing is that one good question that we can ask here is the following: why did we rotate this by an angle of pi over 4? Okay, so why this? It ended up being in a better shape. Okay, maybe we were lucky, but the first part, which shows some positive signs, is that in here we could diagonalize the matrix. Okay, so and then we also know one thing. We know that whenever we multiply a matrix with a vector, what happens? So a matrix A, when this one operates on any vector, what this does is that this rotates the vector, right? And the second that it does,
it changes the length.
That's correct. So it changes the length change. Okay? It can expand it or it can make it shorter. So this is what happens. Now, I assigned a question from last week where I said to you, get the matrix A, okay, and which I forget. I think it was something like 1 minus 1, 0, 1, or something else. And I said to you, find a vector AB such that when you multiply this matrix A with AB, you find the vector CD, and the angle between these two vectors is 120 degrees. Okay, this was one question that we provided. So it looks like if A and B change, even if it is the same matrix, we're going to get different angles between any two subsequent vectors. Now you are following this class, and you remember that this A, in fact, what it was, this was A cubed was equal to the identity matrix, which in principle, this is something like identity matrix. It rotates the angle of a vector by 360, which means that it brings it back where it was. And the A, in this case, on average, is going to be 3 different angles times 120. Okay, so think about this one, think about this matrix. I'm going to erase it very soon, but what we want to say here is that for any specific A, there exist some vectors which don't rotate. Okay, so when you apply those x's, so it's going to be an expression like this: any matrix A times x. This is going to be equal to x. The direction is preserved; it is the same, but we cannot constrain also the length change. So for the length change, let's write it like this. Okay. So then the question is, now we are kind of reformulating the question. The reformulation of the question is the following. Given A, so the new question, given A, find x, okay, and find lambda. But find x such as what? Find x such that A cannot rotate it. Okay? And then let's see how we can solve this problem. Now this was a reminder from last week's assignment. So how can we come up with a vector which does not rotate? Then let's look for the solution. What we can do is that we can say A minus lambda times the identity matrix times the vector x. This is equal to the zero vector. So where have you seen this equation before? What is this? Solving this system, what does it mean? This is finding the null space of matrix B, right? And the matrix B is equal to matrix A minus lambda I. Okay, so finding null space. So what is the solution for this equation? What is the first solution? The first option is for x to be the trivial solution. So we can say B times 0 is equal to 0. But we don't want the trivial solution. Okay, this is fine, but we want x different from 0. And value of x is different from 0 when? Only if the determinant of B is equal to 0. Now, anyone in the class can explain this to me. Who can explain this to me or to us? Why x is different from 0 only when the determinant is equal to 0? You can raise your hand in the comment section if anyone wants to answer. Yes, Ari?
Well, I think if determinant is different from 0, we will have a free variable.
Yes. Well, yes, we can say so.
Then the solution will be probably a line if we have a free variable. So we will have a solution different from 0.
Okay, Ari, think for a moment like that. Wait a second. So you are saying that the term is 0, then that means that we have a free variable equal to 0. Then, do you remember, Ari, that we have said that in any matrix, if one row is full of 0, what is the determinant?
It's 0.
It's 0, that's true. Because we can find the determinant by expanding the matrix along any one of the rows or any one of the columns. So if one of the rows is 0, that means that, how did we get it? We remember that when we used to find the reduced row echelon form, starting from a matrix, we used to do some operations with the rows. And sometimes, if one of the rows was linearly dependent with the other rows, which means that it can be written as a linear combination of the other rows, that means that it's linearly dependent. That means that in that case, we are going to get very easily a row full of zeros. Okay? So starting with a square matrix, try to convert it in a reduced row echelon form. If we get one full of zeros, that means that one of those vectors or one of those rows, it was linearly dependent, which means that the determinant is going to be equal to 0. Why? Because so let me write an example. I'm going to erase this one. 1 minus 1, 1, 2, 0, 2, minus 1. So this is the first column, the second column. If I write the summation of these two columns, like -1 plus 0, this is -1, this is 3, this is 1. The third row, this column is a linear combination of these two, okay? And which means that this is equal to 0. The solution here, so if we do here a solution of A, B, C, if this is equal to 0, then we know that the determinant is equal to 0, but what is the solution here? This is A is equal to 1, B is equal to 1, C is equal to 0, wait a second, C is equal to -1. So in this case, we know that this is a solution. It is different from 0. It is easy for us to know, because this means that we can obtain a linear combination of the columns to get a 0, right? So think about this one again in the way that we used to think about the null spaces. But it is obvious that the vector x, in principle, it is going to be a linear combination of the columns of B. So now let's try to solve this problem. Then let's try to figure out which vectors are not rotated. So let's start with the matrix A, which is 5, -3, -3, 5. And let's write this one. So we get 5, -3, -3, 5, minus lambda, 0, 0, lambda. Okay? What is this? This is 5 minus lambda, -3, -3, 5 minus lambda. Okay. Then we have this expression, and we have to find the solution for lambda, right? Because this is as much information that we can obtain, and this is 5 minus lambda all squared minus 9. This is equal to 0. Okay, this is equal to 0. Then if we expand this one, we're going to get lambda squared minus 10 lambda plus 25, because 5 squared is 25, minus 9 is plus 16. This is equal to 0. Now, this is a polynomial of the second order, and as a polynomial of the second order, we expect to get two different solutions. Now, allow me to take this out for a moment, because we know that we just wanted to show that this is equal to this. And let's continue in here. So we have to find, this is a polynomial of second order, we need two solutions, and this one, the same equation, it can be written as lambda minus 2 times lambda minus 8, this is equal to 0. So it looks like the first lambda is 2, and the second lambda is equal to 8. So in this case, we say that for lambda equal to 2, we are going to get what expression? Let's read this one carefully. Ax is equal to lambda x. Now, for a matrix which is 2 by 2, what can be the dimension of the vector x? Ari?
Once again, please. I did
2 by 1.
A is 2 by 2. So what should be the dimension of x?
2 by 1.
That's correct. Okay, so here we have 5 minus 3 minus 35 times AB, and this is equal to, what is this? This is 2A. Sorry, this is 2 times. This is 2 times AB. So, I saw Anissa Mehta, I think it was, Anissa that had raised the hand. She's still here. Okay, Anissa, can you find, what should I get here from as an equation?
So we will get 5A
Yes,
minus 3
that's correct. And then equal to what?
equal to 2A.
This is equal to 2A. Now, how many unknowns do we have here?
We have 2 unknowns.
How many equations do we need?
2.
2. Can we get the second equation here?
Yes, minus 3a
Okay.
plus 5b,
Plus 5b is equal to?
2b.
So it looks like we have two unknowns and we have two equations. And are you sure you have two equations?
Yes, 2.
Okay. So what do we get from the first equation here? Can you help me here?
3a is equal to 3b.
Okay. What about the second?
So a is equal to b.
What about from the second equation?
We will have minus 3a is equal to minus 3b.
So did we really have a second equation?
No, we have the same. A is equal to b.
So in fact, whenever we try to solve these types of equation, if we find only one, it's enough. Okay, don't go after the second one because the second one is linearly dependent. Why is this the case? Because we said that we know that this equation is valid for determinant is equal to 0. So that means that one of the rows, it's a linear combination of the other rows, right? So we don't really, which means that you think you have two equations, but you really don't. You have only one. So in this case, if we get A and B, so Anissa, can you give me a pair of A and B which satisfy this condition?
2, 2, 1, 1.
1, 1. That's correct. Okay, let me write 1, 1 here. This is 1, 1. We found it. Then let's try to find the same thing for lambda equal to 8. Here, the equation is going to be 5 minus 3, 5 times AB. This is equal to 8 times AB. So what is the first equation we get from here? Anissa, you can answer again.
Yeah. 5a minus 3b is equal to 8a.
Now, do you have a second equation? Forget
We
it.
will have the same one,
You
I
don't.
think.
Well, you don't have a second equation, but you can check, and we can check it together, of course. We can say minus
3a plus 5b is equal to 8b.
8b. The first equation, what do we get?
Is 3a is equal to minus 3b.
Okay, what is the other equation?
And minus 3a is equal to 3b.
Which means that you really didn't have a second equation, which means that now what could be a pair of A and B which satisfy this condition?
1 and minus 1.
That is correct. So minus 1 and 1, that is a pair of numbers which do satisfy this condition. Okay, and yeah. So it looks like we were looking for. Let me think for a moment. We were looking for vectors which cannot be rotated by this specific matrix, and we found these two vectors. Now, we are going to claim, for a few reasons, that these vectors that we found out here, they are this P matrix here. Okay? So this is going to be the matrix which conducts the transformation from one basis to another. And by the way, if we look carefully, these two vectors, they are already here, which is the rotational matrix. So we use this matrix here, using as a basis these two. So then this means that, oh, okay, so apparently the two vectors which the matrix A cannot rotate, apparently they look like they can constitute, so they are linearly independent first of all, because these two are linearly independent. If we draw them, this is how they look like. So 1, 1, if we draw here in this domain, using the standard basis as a reference, this is 1, 1, and minus 1, 1 is this other vector. The angle between these, it is 90 degrees, okay? And the angle between the standard basis, it was also 90 degrees. So it looks like this new basis, or rotating the original standard basis by 45 degrees, in principle, this is what it is. And now, the question is the following. If this if this is the matrix A, right, and this is the matrix P, we can ask the following question: what is D? So the question is, how does this matrix here look like? What did we say in the previous session? We said that the matrices which conduct the linear transformation, they are equal to what? What is D? How did we write D in the previous hour?
P inverse A and P.
That's correct. What is P inverse? P inverse, we can factor out, so let's assume that this is the P, okay? What is P inverse? P inverse, let me think for a moment. Let's write 1 over square root of 2. So we have this matrix. The inverse of this is that we change the numbers 1 and 1, so we interchange them, and then we change the places here. So it's kind of, we take the transpose, okay? So the P inverse, you can correct me, but this looks like it's going to be something like this. This is 1 and 1. Then we multiply with the matrix 5 minus 3, 5 minus 3, minus 3 and 5. And then we multiply with the P now. P again, it's 1 over square root of 2. So allow me to do this on square, okay? It's 1 over square root of 2 squared, because we have, this will appear again here. This is going to be 1 minus 1, 1, 1. Okay? Now let's try to find what this is. So the multiplication of these terms here, this is equal to 5 minus 3 is equal to 2 probably, yes. And then we have minus 5. What is this? Minus 5 minus 3, this is minus 8. And then we get minus 3 plus 5, this is 2. And this is 3 plus 5, this is 8. This looks like correct. Yeah. And then we multiply by 1, 1, minus 1, 1, and this is 1 over 2. And then here, this will be equal to, let's preserve this 1 over 2, and we have 1, 1, 1, what is this? This is 4, okay, because we have 2 plus 2. Then here we have, let me take this out, this x here. This is 0, and this is 1, 1, this is 0. Minus 1, this is 8, plus 8, this is 16. So finally, what do we get? 2, 0, 0, 8. So it looks like the matrix which can represent the matrix A in the standard basis is going to be 2, 0, 0, 8, which we can write it here, 2, 0, 0, 8. And have we seen this matrix before? It looks like we have seen this matrix right here. Okay, and this matrix, it is also obvious because it is having in the diagonal terms, it's having the eigenvalues. Okay, so we have this matrix here. We found the eigenvalues. The eigenvalues were 2 and 8. We can immediately write them into a diagonal matrix, 2, 8 like this. And we prove that, and again, and how can we conduct? So this, again, we start with this matrix, we put eigenvalues here, but then the question was, what is the basis? The basis is composed of these two vectors, which the matrix A, it can never rotate. So if we multiply this matrix with one of the bases here, this will not be rotated, it will be preserved, okay? It's like a major axis. It is the basis, which is the best possible basis for this specific matrix. If we change the numbers, if we give another matrix A, we can still find other vectors which are not rotated, but or which the matrix cannot rotate. If we find those, these are called the eigenvectors, and they can be the best basis. We have said a few times that for any standard basis, we can find an infinite number of different bases, other ones, but which one is the best one? You just go after these specific vectors that satisfy this condition. Now, this is what I wanted to say. So here in the board, we see one identity which is given, of which we can simplify or making it a little more intuitive by changing the basis, and then it makes it much easier for us to draw an ellipse. And then later, we got the work done somewhere here, and then we tried to represent the problem slightly different. And we ended up finding these parameters, which were these lambdas and the x's, and we found also the same answer, but looking from a different perspective. Do you have any question for so far? No question? So now, these elements that you see here on the board, what they really are, these are the eigenvalues and the eigenvectors. And one of the most important equations in linear algebra, it is this expression right here, and this board, it will soon go away. So for any matrix A, we can rotate it, we can change the length, but if we have such a condition, we call this one the eigenvalue. Eigenvalue equation, which means that there are some values which are called inherent values, osevlerat vetjake, inherent vet matrices, and from the eigenvalue equation, it can help us to identify the eigenvalues, which are identified by commonly using a lambda, and the eigenvectors. Which would be this x. And traditionally, what we can expect is that for each lambda, we might expect a specific eigenvector x. So assume that if we have a matrix A, which is 2 by 2, such as in our case, often we might expect to have a lambda 1, and then for this lambda 1, we have to find an x1, okay? And for that, we can also have a lambda 2, because the polynomial that comes out from when we equal the determinant of a minus lambda I equal to 0, in this case, we get a polynomial of the second order. We expect to have two different solutions. If the two different solutions of a polynomial, they are different, then we might also do, for lambda 1, we have x1. For lambda 2, we might expect another vector x2. We might also have more lambdas from our characteristic polynomial, but this is the general approach. And we are going to see also other cases when we have more than 2 lambdas, or when the lambdas are the same, because the polynomial of which we want to solve, it can also have this form. It can be lambda squared minus 4 lambda plus 4. This is equal to 0. So in this case, this is lambda minus 2 squared is equal to 0, which means that lambda 1 is equal to lambda 2 is equal to 2. Okay? And so the general approach is going to be something like this. So here we have lambda is equal to 2, and we found the eigenvector. Okay? And here we have lambda equal to 8, and here we found another eigenvector. And we use that eigenvector for the basis of the new domain. Okay? If you don't have any more questions, we can end this session again.